All right, let's get started with the Trust and Confidence panel. The moderator for this panel is Charles Palmer. Charles serves as Chair and Director of Research at the Institute for Information Infrastructure Protection, or I3P, at Dartmouth College, where he's also a visiting professor. He's Chief Technology Officer for Security and Privacy at IBM Research. Charles was named a Distinguished Engineer of the ACM in 2006 and is a member of the Department of Homeland Security's Data Privacy and Integrity Advisory Board, and he asked me not to read any of that. So, Charles, you're up.
Yes, good afternoon. So, trust and confidence, we're not really sure what that means, any of us. If you ask each person, you're going to get a different definition. Well, I got one here too. Trust and confidence, who knows what that means? The stated discussion is ensure the value to society of cyber systems is not limited by a lack of trust and confidence. Assure that data and resources can be reliably used for their intended purposes. That's a big order. I'm not sure we can do that in the physical world, but as we increasingly transition everything that matters to the not-so-physical world, perhaps we should at least give it a shot. So whether it's information security in general, data management, identity, trying to get rid of all the passwords we have, I mean, there's all of these things or aspects of trying to get this right. Because at the bottom line, what we're trying to do is figure out ways to trust strangers. And we don't really always have a good way to do that. So it's far more interesting to listen to the other folks on the panel than me, so let's get started. I'll begin with Jeanne Spafford. Everybody knows Jeanne. And you won't be surprised that he gave me a different introduction to use rather than the one that you have. So you can read that one at your leisure. Here is Spaff's introduction. There is often a fine line between vision and insanity. Representing that ambiguity is Jeanne Spafford. He is professor of computer science at Purdue University, and to some he is a polymathic futurist. And to others, he is an iconoclastic crank. To us, he is our first speaker. Jeanne?
Thanks. I have some overheads here. Do I bring them up on the laptop?
Yes.
All right. That means I have to put on my glasses. And as I'm doing this, I don't know if Sujit was going to say this during his talk. Okay. But one of the problems to address in this arena is the fact that protection of information and processing is not viewed as a first-class property. That is, it is not a portion of the design of systems. It is added as an afterthought, so therefore it is perhaps fitting that we are the last panel, perhaps an afterthought in the program. And all credit to Sujit for that observation. But to structure my initial comments here, if we look at an overall conceptual flow of software development, procurement, use, and disposal, or computing in general, let's not limit it there. We start off with policies, laws, needs, other kinds of things. Those flow into requirements for what we would like to build or acquire. We then develop or procure, or both, items necessary to meet those requirements. And unfortunately, we don't do a good job all the time, and sometimes we end up with things we didn't expect. We have to go through a process of validation and verification. And if we have purchased something from a third party, we may also want to be doing some assurance to be certain that we got exactly what we asked for and not something extra. Then we put it into operation and all that's involved with operation, including patching and maintenance of that artifact. If something goes wrong, we have to respond to the incidents. And that doesn't necessarily mean malicious incidents. It could be environmental incidents, that the power goes out, for instance, or some other kind of problem, but we have to respond. We have to somehow deal with the loss of operation. If we care about why that happened, we're going to do some investigation and forensics. Why did the system fail? Was it a flaw in the software? Did somebody plant something in the software? Did a user misunderstand and type the wrong commands? And eventually, when we're done with the systems, we need to dispose of them properly. And this is a whole range of issues. Certainly in the area of confidential information or classified information, that has to be disposed of. But we also have bigger issues, environmental issues, green issues, where we dispose of a great deal of electronics components, and there's toxic material in much of what we dispose of. So all of this is sort of a big picture view. Now, if I focus in on the protection, the security aspects, these four areas have received undue influence and, to some extent, I believe, an abundance of funding to address issues, perhaps not completely successfully. In particular, patching and maintenance are sort of viewed as synonymous, that we now structure some of our operations around monthly patches. I was making a joke to somebody that as you all enjoy your lunches, if you look at the label on it, I hope you don't get viruses from your Windows lunch. But we are constantly facing that patching case. We have operational security issues we've done work in, and some focus on static testing, a little bit of dynamic testing, and a lot on incident response. But I think we need to pay more attention in some other areas. So up front in the requirements capture and development process, we need to do a far better job of building quality software. Some of this may be under the rubric of software engineering, programming languages, but I'm thinking even more fundamentally than that. The operating systems and the architectures that we use could be done differently. Many of the artifacts that we've been using were originally developed when computers were extremely expensive. There were few of them and we had to share them. Memory was scarce because of the cost, and secondary storage was slow to access. So we developed concepts such as time sharing, paging, and similar kinds of things. Those are still present in our systems today, and yet many of you, for instance, with your laptops, have enough memory in them, you never page. But we're paying for all the circuitry and all the overhead and all the software for things that we don't use anymore, and the technology is continuing to advance. We need to go back and fundamentally revisit some of our assumptions and our architectures. We need to do a better job of building quality systems that are resistant to not only flaws that someone exploits, but flaws that just simply occur. The two aren't really that different. Second area, a little bit more on the V&V, the testing, perhaps a little less on some of the static testing, and a little more on dynamic testing. But specifically, assurance is a huge problem. And this sometimes is referred to as the supply chain security problem. We buy things from a number of sources, and we're now in a global environment. How do we know what is really in that software? How do we know what the hardware really does? How much should we trust those things we have obtained from third-party sources? We do not have good answers. We don't even know how to phrase the questions precisely. This area is in need of a lot of research. And then at the back end, if all we do is continue to patch our systems and build spam filters, the problems are going to get worse. We are doing a pathetically poor job of law enforcement, of investigation and prosecution. I don't know that there are any law enforcement entities that are a member of NITRD, but they don't have the tools. They don't have the funding for the tools. They don't have the community who knows what tools they need. We can certainly do a better job of providing information on attribution, evidence collection, presentation, capture of what's in storage, network traceback, and other technologies that are going to be of incredible value to law enforcement and as well perhaps to military intelligence and large organizations trying to find out where are the proprietary information going, who's taking it, and why. Some other issues that underlie several of these things, we don't have any good security metrics. This has been listed as a grand challenge in nearly every grand challenge exercise done in security over the last decade. It was part of the PTAC report. It was part of the CRA grand challenges. It was one of the InfoSec hard problems list. We have not made any progress. And I would contend that part of that is that we do not have a sound set of underlying principles. For those of you who've taught a class on this or looked at it, we have the traditional CIA model, the confidentiality, integrity, availability model. But those are not independent measures. And therefore, they don't define a metric space that's really usable because they have dependencies that we don't completely understand. The concepts are, but we can't build metrics around them. So we need to do something very fundamental in terms of identifying concepts that we can use to then build metrics to say, is it worthwhile to use this system or to make this change? Will it pay us back? Or is this configuration more secure than another system may be? Second issue, privacy is critical. I think we generally acknowledge that. The problem is that many people who advocate better security think that that means we have to reduce privacy. And it isn't the case. The two are not coupled so that if you increase one, the other goes down. It takes extra effort to find how to do it. And again, that's a matter of research, is what are some methods that we can use to increase both. Privacy should not necessarily overrule better security, but we have to acknowledge that without good security, we can't have privacy. So the two are connected, but they don't drive each other. Third, if we're talking about research, the first thing we have to do is get away from the mindset of it would be too expensive to retrofit, or it won't run on Windows, or I can't do it with Intel chips, or whatever mantra you may hear that I hear far too often in review sessions or talking with people in industry and government. It's the wrong answer. That's why we're stuck with a lot of, quite frankly, the junk that we have now that we can't fix, is because people are saying it's too expensive. But we're talking in the background potentially tens of billions of dollars a year lost in fraud, crime, waste, and abuse. We can't afford that either. The lack of metrics makes that difficult. So we have to get out of that mindset. And then last, one size fits all is not the approach. And I would say this is actually true across both days of discussion. There is no single silver bullet. There is no single computational solution in any domain. There are many. And our attempts to push towards a single one-size-fits-all solution means, it's the Procrustean bed that somebody's got to be chopped off at the knees or somebody has to be stretched on the rack to fit. We can do better than that. We're more flexible than that. So my suggestion here to those of you formulating the plan is please leave it open so that there are multiple solutions for multiple problem domains. And with that, I don't know, do we have time or do you want to do it all at the end?
Why don't we try to do it all at the end? Let's be different.
We are different.
Indeed. Okay, so we'll try to do all the questions at the end, write them down. Don't lose that thought. It's always fun to pick on Jeanne. So next we have Insup Lee. He is the Cecilia Fittler Moore Professor of Computers and Information Science at the University of Pennsylvania. He is from Wisconsin, a PhD in Wisconsin, and he joined Penn faculty in '83, has background in undergraduate curriculum, and has another appointment in the EE department. Just one more thing, though. He has served on editorial boards of several journals, Transactions on Computers, Formal Methods, and Real Time. He's an IEEE Fellow and member of the Technical Advisory Group of the PCAST, Networking and Information Technology.
Slide. Okay, so today I'm going to talk about basically cyber-physical systems and some aspect of trust and confidence in cyber-physical systems, okay, what it means in cyber-physical systems. So we have heard cyber-physical systems in the last 2 days. Okay? Let me just start with the definition. Definition in the middle, okay, these are the systems, engineered systems that require tight integration and coordination between computational entities and physical entities. Basically, this is computation and communication core that does monitoring, coordination, and actuation and control of physical and engineered systems. So that is sort of the very broad definition of cyber-physical system. And background for building up to this was we heard embedded system. Embedded systems are becoming more complex, and they are increasingly becoming interconnected, and people are asking it to do a lot more, and then it's increasingly depending on the software. And these systems correctness requires more than just functionality, as to correct with respect to performance, timely, security, and all these nice things. And if you look at the future where it's going, things are getting much more complicated. It's becoming more dynamic, and there are sort of systems of systems, and it's control loops in there. Some are controlled by systems as well as humans, and systems exist. It has to may fail, so it has to self-adapt and self-aware, and so on. So many people believe that there is becoming some sort of phase transition from sort of the networked embedded system to this next generation, very complex cyber-physical systems. And this is actually sort of intersection of real-time distributed system, control system, wireless system, network systems, and some application area. And there are many applications of cyber-physical systems. We already heard about sort of the assisted environment by Philia, and Tom this morning talked about zero-energy building, and Sue talked about sort of the smart traffic systems, and then also sort of the Tom talked about sort of the smart power grid, where system not only going to do distribution of power, but each household may become a sort of generator spec, and depending on the time of the day and demand and supply, it may actually try to sell the energy into the system rather than consuming it. So there are lots of interesting sort of complex future systems. One system that I'd like to say a little more is this healthcare, because there was again mentioned by Tom this morning. It's a healthcare system. There are medical devices. Currently, they are all sort of working along, and this picture right here is trying to represent future, sort of the operating room of the future, where medical devices are interconnected and talk to each other, and so on. And so there was sort of the very simple example or case where the malfunction of certain sort of medical device has made patient die, whereas if you made this medical device talk to each other, you could have avoided it. So there's a big effort to trying to make a medical device connect to each other, talk to each other, and work together. And this is a big challenge. Now, there's a nationwide sort of effort to have this electronic record system. Now, this electronic record system has to talk with medical device. So a medical device needs to talk with such a system to get a patient information, and it can be some sort of, and also collect the data to populate this electronic medical record system. And this is going to be the examples of a future sort of the cyber-physical systems. And the picture here is there are many, many different application area, and what's sitting in the middle as common core is cyber-physical systems. And there are some defining characteristics. Basically, cyber-physical systems deal with interact with the sort of the environment and physical world, and it's going to have lots of sort of the entities in there. So scalability is going to be a big defining factor, and these systems are not going to be built from scratch. It's going to be built as a system of systems. So that's going to be a defining characteristic. Also, there's interaction between communication, computing, and control. So this represents convergence of these three different areas: computation, communication and control. And there is this unprecedented need for, I guess, security and privacy. And this security and privacy has to not just talk about the cyber aspect, you have to also talk about the physical security, and this has to be integrated together. For example, if you're talking about, say, next generation sort of the refinery where everything's controlled by wireless systems, then you have to combine this notion of security in terms of cyber as well as physical aspect and the human aspect as well. And all of this thing has to be working in working dependably and may need to be sometimes certified. So the question really becomes, trustness is, how can we build the cyber physical system that people can trust? Because these systems are life critical, safety critical. And we need to make sure such systems are reliably operating and safe and secure and so on. And if you look at the history, any complex systems, there are many, many well-known failures. Some were extremely expensive in terms of monetary cost, and some actually caused people to die and so on. So future cyber-physical system, unless we develop the foundational aspect and how to build it right, it's going to cause this kind of, it may experience this kind of problem. And many of this problem is because systems are complex. And systems are complex because it has interacting components. When components interact, then there's some sort of unexpected consequence as well as sort of expected consequence. So according to this author, sociologist Charles Perrow, his book on normal accidents, he points out any complex system which is sufficiently complex can cause an accident due to interactive complexity as well, interactive complexity and tight coupling. So whenever we try to build this kind of cyber-physical system, the challenge is this system will be built as sort of system of systems. We need to compose systems, so we need to really make sure when you compose it, it maintains the right properties. That's what it means, the compositionality, and try to avoid this unexpected interactions. And another aspect during this composition will be systems are very tightly coupled, meaning that if your systems are too tightly coupled, system may fail, and you don't have time to recover this from this failure, and then it can cascade another failure. System as a whole, like a power grid, can come down because of this kind of tight coupling. So we need to really have some scientific understanding of how to address this kind of problem. Okay? And then there are sort of other problems like the third bullet is we need to understand sort of the interaction of human and sort of the physical entities. The human is in the control loop. Some are handled by system, but some are handled by human. So we need to understand what is the user's, say, mental model versus what system is providing, try to see how to make a system safe in this respect and so on. So there are lots of issues, and you can find much more detailed information from this website. This was the CPS Summit, and there was a summary report. Okay? So to have CPS of the future, we need to train workforce. And this sort of requires slightly different kind of a curriculum than what we are used to. So this actually has to combine different aspects. So this curriculum has to be somewhat interdisciplinary, and we need to teach not only discrete mathematics and also continuous mathematics, and we need to teach foundations of computer science, some aspect, formal method, but also control theory, feedback control, and then we have to teach how to develop high assurance software. And then there are some other aspects, and you should have a nice hands-on project so that we can attract students. And this potentially presents great opportunities. There is a great potential for that once we have such a systems, okay, there where physical system can be sort of remotely accessed and controlled. So it provides some locally physical system through some sort of virtualization. You can globally access it. And I think there may be some applications that we don't see at the moment. So it may actually change how we interact so it may actually, like internet has changed how we interact with the humans, okay? And then this may cause it. Okay? So let me have one last, and then also how we engineer the system. And this is something I really like to point out is this sort of, there has been a lot of activities. There has been a lot of workshops starting from 2005, okay? And you can get the list of workshops here. And initially, it wasn't called cyber physical system. It was just a workshop on high confidence software systems. And then NSF coined the term cyber physical system. And there is a sort of community building effort. And there's a CPS Works 2009 with conference on real-time sensor network and hybrid system. And this is international community. This will be held in Europe next year. And there is very strong support from Europeans and Asian countries. Sorry.
Very good. Thank you, and so thank you. Yeah, that composition problem is a real stinker. So next we'll move on to Dr. Ray Vaughn. He's the William L. Giles Distinguished Professor and the Billy J. Ball Professor of Computer Science and Engineering at Mississippi State. Prior to his joining the university there, where he does research in software engineering and InfoSec, he was 26 years in the U.S. Army, finishing out as a colonel, and then he went to be vice president of DISA Integration Services at EDS. He's also the current director of the MSU Center for Critical Infrastructure Protection and the Center for Computer Security Research. Right? Good stuff.
So I promised to keep us on time, but I really want to thank Chris for not putting me on Emergent Cognition or Beyond Virtual, because I had absolutely no idea what those meant. But I do think that I have some idea of what trust and confidence means. As my Army experience taught me, we don't think much about trust and confidence when we're building systems. I was the Army's senior software engineer for a number of years. We built Army business systems. I never recall thinking about security, trust, assurance, or any of those things when we put the system together. I remember thinking a lot about those things after the system was fielded, and that's the wrong way to do things. When I worked at the National Security Agency in the old National Computer Security Center, I thought that formal methods and modeling were the solution to computer security. And then I was taught by a colleague from Georgetown, now with the Naval Postgraduate School, Dr. Dorothy Denning, that going down that path would lead to, I think she said, dreadful systems that no one would ever use. And we funded some of those systems out of NSA, and sure enough, they were dreadful and no one ever used them. She also taught us that people tend to hack the systems from outside the technical solutions that we bring to the table, and that too was something that we need to think about. So my thoughts are perhaps this whole issue is not really an issue for computer scientists. I think this is very much an interdisciplinary problem that involves the focused knowledge, critical thinking of scientists from a wide variety of fields, not just software engineering and computer security or computer science. So I think it's important for us to, first of all, remember that we haven't done a very good job in the last 40 years of solving the problems that were identified very early on. The basic problems in trustworthy computing, as I think Dr. Spafford pointed out, are still basic problems in computer security, and they still represent a research challenge. One of the newer research challenges that we still haven't done a very good job on is anonymity on the internet and our ability to obscure one's identity. That's extremely problematic. And what really caught my attention was when I was recently working with Air Force Cyber Command, I saw in some Air Force documents the idea or notion of a kinetic response to cyber attacks. Think about that. With anonymity on the internet and the ability to spoof and change where a packet maybe came from, a kinetic response should be a bit frightening. I also believe as INSEP pointed out, that high assurance, trustworthy software and hardware in non-traditional computing devices within the critical infrastructure is a serious challenge, and I think it's one that we need to be addressing. These are quality of life computing devices, critical infrastructure systems, and we sometimes call those process control systems, industrial control systems, SCADA systems, or a number of other names, but they actually apply to automotive systems or quality of water, HVAC systems, our personal safety, and the list goes on and on and on. So I want to remind the panel and remind NITRD of the very first research agenda that I'm aware of, published in 1970, which the U.S. government immediately classified secret when it came out, and this was published by Dr. Willis Ware out of the RAND Corporation. He said this is what we need to do in computer security, facilitate progress toward an open environment. That's an environment where untrusted users over untrusted pipes can communicate in a distributed way with computing resources and do that safely. Improve the understanding of failure risk, what happens when our systems fail, what vulnerabilities does that introduce. Improve the efficiency of security controlling systems. That is, what happens when a system fails? What does security do to the speed of the system? I did a little work in high-performance computing security, and I discovered that the high-performance computing community doesn't think about security first. They think about speed first. Imagine that. Vulnerability analysis is still a problem, and the cost of security is a problem. And then Willis suggested that we try to solve leakage points in the areas that you see on this slide, and I think all of those areas still represent significant leakage points. So as far as the investments that I would like to see, I really appreciate and support the increased interest in cyber-physical. I might point out that that is the one topic I heard every single panel and the guest speaker talk about today, and it continues to be something that's very popular with all of us. I think we all agree that a continued investment in cyber-physical is absolutely essential. I want to suggest that continued investment in education, particularly information assurance education, is important in our universities, continuing to develop curriculum, capacity, and research efforts in that area, and the facilitation of more academic, industrial, and academic government partnerships. Now, we've heard that from a number of panels, too, but I got to tell you, if that was an easy thing to do, we would have been doing that a long time ago, because we all agree that's a good thing to do, whether you're in industry or academia or government. But the reason we don't do that today is because there are many barriers, and I think that maybe suggests that a separate panel or discussion group might need to be created to look at what those barriers really are and develop some actionable kinds of things that we might be able to do to help facilitate that. Now, to keep with the tone that I've heard in the other panels, let me skate to where the puck is. Now, I heard a lot about pucks, and I'm from Mississippi, and we don't do a lot of pucking down there in Mississippi. I have no idea what we're talking about here, but I think that I figured it out. So where the puck is today is this kind of a system. Please look at this. This is what we call a SCADA system that is full of remote terminal units and process or physical logic units and SCADA servers and modems. And that's not the important part. The important part is where it says corporate internet connected to market systems. So this means that we're taking systems that control physical processes and we're using real software, not embedded software. I'm talking about software running on a Microsoft operating system on a laptop somewhere to control those physical processes. And the operator that's controlling them is using a virtual environment to do that. But that operator actually sets different set points on that system and can cause damage to the system. Now, because we have it firewalled off, we would assume that it's safe, but most of us realize that firewall is something that you can screw up very easily, and when you do that, you create a hole, but you also create a false sense of security on the other side of the firewall, thinking that the hole doesn't exist. So some things that concern us today in the cyber-physical systems world Is it typically data sent in clear text? There's a heavy use of unsecured wireless. Protocols are not robust at all. We use protocols like Modbus and DNP3 and a whole list of others. Data can quite easily be changed or repeated, and we have been looking at this in our control systems lab for some time now. We've demonstrated all of these sorts of problems, and they are very easy to demonstrate. They are connected now to corporate networks, and unpatched software, improperly configured software, inadequate physical protection, and the list goes on, is quite normal in these environments. And the reason it's normal in these environments is because the control systems, process control community has not grown up in the same way that the IT community has grown up. So I feel a little bit like an anthropologist that just discovered a lost tribe. This is wonderful for us because we know how to solve these problems. We've been looking at it now for about 15 years or so. And so maybe, actually we've been looking at it for like about 40 years. But maybe we can use some of what we've learned in this community. So to move on to where the puck is heading, I think this is where the puck is heading. We will be using our PDA devices or our laptop from anywhere in the world to control those physical processes. Unfortunately, the way the software is configured today, someone else from anywhere in the world can use those PDAs or laptops to control your physical processes, and that scares us a great deal. So we've been looking at a lot of vulnerabilities in current HMI software that runs these systems. We're finding a large number of vulnerabilities, and we are finding it very, very difficult to work with the vendors to mitigate the vulnerabilities, and very difficult to actually get them reported to the community that needs to know. So that's my opening statement, and I'll turn the podium over to Sujit.
Okay, thank you, Ray. Thank you for that dose of reality. Next, we have Dr. Sujit Shenoy. He is the F.P. Walter Professor of Computer Science at University of Tulsa. He's a very busy guy in cybersecurity and digital forensics, and PI on projects supported by DHS, FBI, ICE, NSA, NSF, and the Secret Service, as well as a little bit of time left to be editor-in-chief of the International Journal of Critical Infrastructure Protection. For almost a decade, Dr. Shenoy has spearheaded the University of Tulsa's Cyber Corps program, which mainly trains MacGyvers for the intelligence community. If you don't know what a MacGyver is, that's a good question for break. He's also the director of their Cybersecurity Education Consortium. So, Dr. Shenoy.
I'm passionate about many things, but I'm going to share with you 3 of my musings today about things I'm very passionate about. I've been working in these areas in these 3 areas for about 10 to 15 years. Some things have worked, many things have not. But what I'm going to share with you now over the next 10 minutes or so is what I think ought to happen. And you can ask me in the question and answer session later on about the things that worked and those that didn't. One of my former students, the futurist Daniel H. Wilson, he has a show on the History Channel called The Works, recently published an essay in Popular Mechanics entitled, "Dude, Where's My Jetpack?" He says, the future is now, and we are not impressed. The future was supposed to be a fully automatic, atomic-powered, germ-free utopia, a place where a grown man could wear a velvet spandex unitard and not be laughed at. Our beloved scientists may be building impressive technologies, but some key pieces are missing. Where are the ray guns, the flying cars, and yes, the X-ray specs? I don't care for guns, and that includes ray guns. I'm far too old for X-ray specs. But yes, a fully automated world with flying cars would be quite fantastic. There are numerous R&D challenges to be addressed in microelectronics, material science, and propulsion systems. But I think the automated world of the future will not happen if trust and confidence are not all pervasive. For this reason, I believe that strategic R&D investments related to trust and confidence must cover two broad areas. The first is complex, large-scale systems, cyber systems as well as cyber physical systems. The second is infrastructure, which will allow these complex, large-scale systems to operate. Do you remember the controversy about Reagan's Star Wars initiative? The critics said that we could never guarantee that SDI would work properly. I was a graduate student at that time. And you know what? 25 years later, I still don't think we will be able to do that. We've got to figure out how to build trustworthy, reliable systems and infrastructures, and most importantly, keep them running. We know that complete security is a pipe dream, so our systems and infrastructures have to be resilient. I don't think we're spending enough time looking at resilience, which is extremely important. Most of all, we need to recognize that we are building multifaceted systems of systems, comprising hardware, software, data, and people, operating under myriad technical, organizational, economic, legal, social, political, and ethical constraints. Protecting such complex systems requires creative, interdisciplinary solutions that weave science, technology, law, policy, and of course, economics. If we want to have our solutions actually be applied, we've got to make the business case. The second issue that I'd like to talk about today is workforce development. In 1807, Napoleon called England a nation of shopkeepers. England was a superpower, but it was much too reliant on its colonies for natural and human resources. By the 19th century, end of the 19th century, England was in decline. 2 centuries later, we are the superpower. Our defense budget, discounting Iraq and Afghanistan costs, exceeds the defense expenditures of all the other countries in the world combined. We are an economic juggernaut too, but while our consumption increases, our production of tangible goods has dropped. Years ago, it was automobiles, then consumer electronics, now software. The problem is that outsourcing is rapidly moving up the technological food chain. Are we becoming a nation of shopkeepers? I think the fact is that America's per capita production of scientists and engineers and technicians is dropping. But we can be proud of one thing. We will always have the largest number of lawyers. Do you know what the real difference is between lawyers and engineers and scientists? Well, engineers and scientists generate wealth. Lawyers redistribute wealth. On October 5th, 1957, Sputnik shocked America into action. It changed our educational systems from kindergarten all the way through postdoctoral studies. More importantly, it changed how Americans came to view science and engineering. We have to capture the minds, the imagination of Americans again. Michael yesterday mentioned bumper stickers. I think there's nothing better than a speech. And even better than a speech is a speech that has a name. For example, Old Soldiers Never Die. Even Checkers. Or Tear Down That Wall. Kennedy's Man in the Moon speech did that. He captured the imagination of Americans. I was in kindergarten school in India at the time, and I remember the scratchy recording. Kennedy's speech captured my imagination. My parents were very successful lawyers. That's why I can joke about it. Much to their chagrin, their eldest child became an engineer. Eventually, my 4 younger siblings also pursued careers in science and engineering. I earnestly hope that President Obama will do something to capture the imagination of Americans and others as Kennedy did nearly 50 years ago. He has the platform. God knows he has the charisma. And I think it would be absolutely incredible if NITRD could provide that vehicle. My final musing is about service R&D. Now, I know you're all aware of the importance of service learning. Service learning integrates meaningful community service with instruction, reflection that enriches the learning experience, teaches civic responsibility, and strengthens communities. I sincerely believe that NITRD should invest in what I call service R&D. I think we need to work on R&D problems that can benefit the poor. We should look at ways that networking and IT can improve the quality of human life. Countries in Africa simply cannot afford R&D. Couldn't we craft inexpensive, innovative solutions that will make a difference? I visited South Africa twice in 2007. I met with, listened to, and critiqued the research plan of every full-time student, computer science PhD student in the country. It was not so bad, there were only 25. I even met with a CS PhD student from the University of Nairobi who traveled to South Africa so that he could get some advice regarding his research. The projects were really fascinating. How can internet content be cached to conserve limited bandwidth? How can cell phones be used to receive welfare payments? How can information and communication technologies be used to improve the lives of AIDS grandmothers? These are grandmothers who've lost their children, so they've got to take care of their grandchildren. Those were the kinds of projects that they were working on for their PhDs. I thought it was just fantastic. I think in addition to focusing on service R&D at home, I think NITRD should include an international component. There's a really beautiful story from the 1940s and 1950s. Most Americans don't know about it, but those of us who were born abroad and lived abroad know about it. In the 40s and 50s, the Rockefeller Foundation decided to invest in research in crop science. And they recruited some of the best American agronomists and had them set up a research center in Mexico. That was in the 40s and 50s. That research in the 60s helped save 1 billion lives. Again, 1 billion lives. There was really no need for America to work on wheat, on that kind of wheat. It was semi-dwarf, high-yield, disease-resistant wheat varieties. Our soil is rich, our climate is excellent. But America did, because that's what great countries do. The agronomist Norman Borlaug from Iowa, who led the R&D effort, won the 1970 Nobel Prize. Not for chemistry, but for peace, which of course is the greatest prize of them all. Let me conclude by saying that we should look at NITRD as an opportunity to really make a difference. I think it would be awesome if we could dream big dreams. Thank you.
Now I get to talk after that. Oh. Thank you, Jeanne. Another topic that we've touched on here and there, it's not just the only one that's left on this panel. It's probably the scariest one of all. I like to say it as people are the ultimate critical infrastructure. At the end of the day, as my dad would say, the nut behind the wheel is going to make that decision, whether they're driving a car or deciding whether or not to click on that, yeah, sure, that looks like a good certificate. Or more likely, I have no idea what that is, it's in the way, I'll click on it. So people are what we have to worry about. They make mistakes, we all do. Specification of things that we want the system to do, the design of that system. Of course, we all know we mess up the implementation. 40 years of buffer overflows, and we're still perfecting that. Deployment, repair, and of course decommissioning. It's amazing how difficult decommissioning an application can be. And these people, they have so many conflicting motivations, including BlackBerries. Crush it, please. Disposal. Yes. There's good folks and bad folks and folks that don't know that they're one or the other. They are consciously evil or unconsciously / ignorantly evil, make a mistake. And there's all kinds of stresses. If the 3-year-old twins kept me up last night, I would be even less pleasant than I am normally. And clearly, if things happen in your lives, whether it's a financial stress or whatever, your attitudes change. And so I think we all realize people really are the weakest link in this train. One company may buy another, and now they're subject to their set of security constraints or security rules, but it's also the people. So what are you going to do with them? Are these user people problems, or are these design people problems? Everybody's throwing out quotes. I have to include one of my favorites. Robert Morris Sr. gave a talk at Watson once, and I don't know if he said it originally or not, but he said it there. He said, "Systems built without specifications cannot fail. They merely present surprises, usually unpleasant." And as we've said several times, we are building these systems, and at the end, oh golly, let's go tack on a little bit of security. Or my favorite, let's pour a little crypto over that system. And the old steel door on the grass hut image comes to mind. So we have to design all the systems to withstand environmental stuff, but also to withstand the nut behind the wheel. Maybe Pogo was right, those of you old enough to remember Pogo, when he said, "We have met the enemy and he is us." It's our own mistakes. And then on top of that, if you step out of the enterprise world into the world of DoD and government, they have another problem. They don't just have folks out there trying to make a buck, trying to break their systems. They have folks out there trying to break a country, attacking their systems. So even though their staff is typically well-trained and certainly aware of the penalties for abuse, it still happens, and we could go down that list. So even if we do get people to trust something, either through familiarity, like trusting Walter Cronkite, he could have said anything and we all would have said, okay. Endorsement, it looks like the website from my bank. Credentials, I'm showing you something that makes you believe it. Or just necessity. Sometimes we trust things just because we gotta. You want to upload your taxes? Here's the website. You decide. And so that's what we do. When we have trust, though, as some of the other speakers said, sometimes that trust causes you to do things that you really shouldn't do. You trust too much, you upload too much information, you go to Facebook, don't need to say any more there. That email came from Ed, must be okay to click on that link, and so on. So what do? The goal here is to give NITRD some suggestions. Well, I'm from the I3P, and we had some forums last year in DC talking with smart folks from all flavors, academia, government, and industry, to see what they thought were the big deals facing us. And it fits rather nicely that one of those forums was indeed on human behavior and what to do about it. So some of the issues that came up there that I think really are key roles, some of them you've heard before, and you're going to think, well, geez, that's no news. Well, maybe it isn't. We still haven't done things like understand developer and user motivations. What makes people build systems the way they do? Is it because they've always been built that way? Is it because they think that's what the designer or the organization wanted, or they think that that's what the laws require? One of our other projects went out and tried to document all of the convictions in this country that have taken place that are related to cybercrime of some sort. And it wasn't so interesting to show that this percentage of people were caught and that percentage of that number were actually prosecuted, and all the way down to the vanishingly small number that actually do time. We all know that statistic. What was interesting was the wide variety of laws that were actually used. We don't have effective regulations or laws on the books necessarily that people can actually use or know how to use. And so that was an interesting result. So for these people, we have to understand the characteristics of bad actors, past bad actors. Why did they do it? Were they evil? Were they ignorant, untrained, unlucky, or what? And understand the characteristics and context of the past victims. Why did it happen to Jack? Was Jack trusting that email from Ed? Was Jack undereducated? Did the system, the laws, the organization have a failure that enabled a bad act? Don't know. Another topic was understanding the principles of good human-computer interaction and design. not just talking about clicking in the right place and colors and so on, which is important. I learned a long time ago when you replace a process control system in Dead Horse, Wyoming with one that has those cool new tubes, and you replace the old TTY that would chatter. We had two problems. We didn't notice that the chattering is what woke up the third shift guy, and he was also colorblind. And so when we had that cute little soft moan on the screen and it was red, it just put him to sleep. So understanding the principles of good human-computer interaction is key to everything we do. It should be. It just isn't usually, but it should be. But it's particularly relevant in security. A vice president I had at Watson used to turn on every doggone security feature he could every time Windows gave him some more. And then he would call my team, and we would have to go help him turn it off. Always fun. How many passwords do you have? Is this really the best way to do things? Or if we have God's on biometric, who knows what that is? Are we going to use it? Are we going to trust it? Are we going to feel okay about doing it? What's the answer? And then tailoring security. As Sujit said, someone said, there are no silver bullets here. Security has to be tailored to the context and the victim, whoever that might be. Metrics, no kidding. It does come up every time we talk about big challenges. It came up at all three of the forums. The forum on physical infrastructure, on economic infrastructure, and on human behavior. All three pounded on metrics. They're essential to building systems that are secure. Well, okay, maybe that's what we're missing. It would enable more informed purchasing, both by us and by government, and certainly improve deployment decisions on how to do things, how to actually get it out there. And perhaps one of the louder things about metrics at the meeting was it would enable meaningful regulations. Right now we have outcome-based regulations in our minds, but what we produce are prescriptive regulations because we don't know how to measure whether or not you did it. And prescriptive regulations tend to drive us towards a checkbox. Did you do that, Graham? That list of things you're supposed to do? Yep, good, you're secure. Did you think about privacy while you were writing the code? Sure, checkbox. Finally, coordination. And this is another one of those toughies. There's a lot of cybersecurity research going on in academia, in industry, and even in government. Some agencies try to coordinate what they're doing within their agencies. And that's admirable and that's good. That's improved. When viewed across the collection of government agencies, there's a whole lot of opportunities for duplication, omission, and certainly contradiction. This group says one thing and another group says another. So the biggest demand I would place on NITRD would be to be that organization that stands up and looks at all these, many of these folks doing the work are members of NITRD. Do the job of the coordination, help the collaboration be mutually supportive and run in a similar direction as opposed to the alternative.